Hello students, welcome back to my channel where we are studying about Fourier transforms. So in this video, we are going to learn more and explore more about Fourier transform. So we are going to study about the derivative of Fourier transform, the Fourier transform of a derivative, the Fourier sine and cosine transforms of derivatives. So we are going to deal more with the derivatives part. So in the first part, we are going to study about the derivative of a Fourier transform. Derivative in the sense we are going to differentiate the Fourier transform of f of t, right? So we know that Fourier transform of f of t is nothing but f of omega, and that is equal to 1 by root 2 pi minus infinity to plus infinity f of t e raised to minus I omega t dt, right? So now what we are going to do is we are going to find the derivative of the Fourier transform, that is we are going to differentiate the Fourier transform. So let us differentiate this. So we have differentiation of f of omega with respect to omega. So this is equal to, now 1 by root 2 pi is a constant, so we are going to keep it like that, okay? And we take the integration minus infinity to plus infinity, and then we put the differentiation here, that is d by d omega of f of t e to the power minus I omega t into dt, right? So now we are differentiating with respect to omega, so t is going to remain a constant. So what we are going to get after differentiation is f of t is going to remain constant. Differentiation of e raised to minus I omega t is e raised to minus I omega t into differentiation of this. So it is going to remain constant, and differentiation of omega with respect to omega is equal to 1. So we are going to get it as 1 by root 2 pi minus infinity to plus infinity f of t e to the power minus I omega t into minus I t into dt, right? Now integration is with respect to t, so I can't take out the t common out, or I can't take it as a constant, but I can take this minus I outside. So if I take this minus I outside, what will I get? Minus I into 1 by root 2 pi minus infinity to infinity f of t e to the power minus I omega t into dt. Now if you see here, we have f of t, or I'll write this t on the other side, I'll write it here, okay? And if you see this part, f of t e to the power minus I omega t dt into 1 by root 2 pi, this is nothing but f of omega, that is, it is the Fourier transform of f of t. So I can write this as minus I into Fourier transform of f of t, right? But we have one more term here, that is t. So we have Fourier transform of t into f of t, right? Now let's differentiate it once again. So what we'll get here now? So we have the second derivative of f of omega with respect to omega. So this is going to be minus I, right? Minus I by root 2 pi integration minus infinity to infinity d by d omega of t into f of t e to the power minus I omega t into dt. So again, the t's are going to remain constant, and again we are going to differentiate only e to the power minus I omega t. So that again we are going to get it as e to the power minus I omega t into minus I t. So we are going to write it here now. So we are going to get this as minus I by root 2 pi integration minus infinity to plus infinity t into f of t into e to the power minus I omega t into minus I t dt. So when I take this minus I outside again, I'm going to get minus I the whole square divided by root 2 pi minus infinity to plus infinity. T into t is t square f of t e to the power minus I omega t dt. Right? So again, it's nothing but 1 by root 2 pi t square f of t e to the power minus I omega t dt. I can write this as minus I the whole square Fourier transform of t square f of t. So now if I try to generalize this, I am going to get this as nth derivative of f of omega. Nth derivative of f of omega. This is equal to minus I to the power n Fourier transform of t to the power n f of t. Right? So this is what I'm going to get the nth derivative, or in the generalized form, the derivative of a Fourier transform. Or I can write this as minus I into t to the power n f of omega. I can also write it like that. So this is our required answer for the derivative of Fourier transform. So now let's see what is the Fourier transform of a derivative. Okay, Fourier transform of a derivative. So we are going to see the derivative. What is the Fourier transform of a derivative? Not the derivative of the Fourier transform. They will be differentiated f of omega. Here we are differentiating the integral. Right? So with respect to t. So suppose f1 of omega is a first derivative of Fourier transform of f of t. Right? So if this is the first derivative, so what am I going to get? Alright. So f1 of omega, this is equal to 1 by root 2 pi integration minus infinity to plus infinity. Here we are going to write it as d by dt. So we are going to differentiate with respect to t. So this is d by dt of f of t into e raised to minus I omega t into dt. Right? So now to differentiate this, since it is differentiation with respect to t and we have a product, so we are going to integrate it with parts. So when we have to integrate it with parts, we have been seeing that the formula for integration with parts is integration of u into dv is equal to uv minus integration v du. Right? Here we have to apply the definite integrals. That is the other part of the integration. Right? So now, what is u here in this? In this, u is e to the power minus I omega t. And dv is d by dt of f of t. Okay? Now, what will be v du here? Du will be e raised to minus I omega t into minus I omega, because we are differentiating with respect to t. So here t minus I omega becomes constant and dt by dt is 1. Right? So what is v? Differentiation of, or the integration of a differentiation gives me the original term. So if I want to find what is v, I have to integrate this. When I integrate this, I get v is equals to f of t. Right? So this is our u, v, du and dv. So we have to only substitute in the formula. So we have f1 of omega is equal to 1 by root 2 pi. It's going to be a constant outside. So integration with parts here now. U into v. So u is e raised to minus I omega t into f of t minus infinity to plus infinity minus integration of minus infinity to plus infinity. V is f of t and du is e to the power minus I omega t into minus I omega into dt. Right? So what we have here, so if I apply the integrals, definite integrals, I see that e raised to plus infinity minus of e raised to minus infinity, that is upper limit minus lower limit. In both the cases, I get e to the power infinity, which is nothing but 0. So this first term is going to be 0 and 1 by root 2 pi is common for both. Right? So the first term becomes equal to 0. So we have the second term. So what is the second term? So we have f1 of omega is equals to 1 by root 2 pi minus into minus, it becomes plus I into omega. Since the integration is with respect to t, I can consider omega as constant and take it outside the integral sign. So what is left inside is minus infinity to plus infinity f of t e to the power minus I omega t dt. And what is this? Together it is nothing but I omega into f of omega. Right? So what about the second derivative? So if I take f2 of omega, f2 omega is the second derivative of f of t. Second derivative of f of t. So we have Fourier transform of f of t. So we have to differentiate this again. So that is f2 of omega is equals to I omega dy dt of f of omega. That is nothing but again 1 by root 2 pi integration minus infinity to plus infinity d by dt of f of t e to the power minus I omega t dt. Now what do we get again? The same thing we are going to integrate again. So we are going to get back the same thing, that is we are going to get back I omega is already there. The integration of this is I omega into f of omega. So it's going to be I omega the whole square f of omega. So this is going to go on continue. So what we have at the end is, if I generalize this, I have the nth derivative of Fourier transform of f of t is I omega to the power n f of omega. So this is the nth derivative of Fourier transform. So we have found out the Fourier transform of a derivative. Alright? So this is our answer. Next we are going to see the Fourier sine and cosine transforms of derivatives. So here we are going to first define what is the Fourier sine transform and what is the Fourier cosine transform. So we all know what is the definition. So Fourier sine transform is root of 2 by pi 0 to infinity f of t sine omega t dt, and Fourier cosine transform is root of 2 by pi 0 to infinity f of t cos omega t dt. Right? Now firstly we will find the Fourier sine transform of derivatives. So the first derivative of Fourier sine transform I denote it as f1s of omega. Right? So again root 2 by pi is a constant, 0 to infinity d by dt of f of t sine omega t dt. Now we have to follow the same steps as we have followed in the earlier part. So we are going to integrate this by parts. So what is that? Now again we write the formula here. Integration u into dv is equals to uv minus integration v into du. So what is u? U is sine omega t and dv is d by dt of f of t. So what will be du here? Du will be differentiation of sine omega t, that is cos omega t into differentiation of omega t. So we get it as omega, right? Or we can write it as omega cos omega t. And here, what is v? V is nothing but f of t. So let's substitute all of this in this formula. So we get f1s of omega, this is equal to root 2 by pi is common out, right? U into v. So that is sine omega t into f of t, or I'll write f of t into sine omega t, the limits from 0 to infinity, minus, I'll take it down here, integration v into du. The integration is from 0 to infinity. So we have v is f of t and du is omega cos omega t. Omega cos omega t dt. Okay, bracket close. Now here, what will be the value of this when I apply the limits? So we here see that t tends to infinity, f of t tends to 0. So when t tends to infinity, f of t tends to 0. So this particular part is going to become equal to 0. And what is left here is, we are left with root of 2 by pi, omega is a constant, I bring it out. So we have 0 to infinity, there's a minus here, 0 to infinity, f of t cos omega t dt. Now if you observe, root 2 by pi 0 to infinity f of t cos omega t dt is nothing but fc of omega. So I can write this as minus omega into fc of omega, right? So this is the Fourier sine transform's first derivative. Fourier sine transform of first derivative. So let's see what is the Fourier cosine transform of the first derivative. Now the Fourier cosine transform of the first derivative I denoted as f1c of omega, and the same steps again. So root 2 by pi 0 to infinity d by dt of f of t cos omega t dt, right? So again we are going to integrate by parts. So what is our formula? Integration of u into dv is equals to uv minus integration v du, where u here is cos omega t and dv is d by dt of f of t. So what is du? Du is minus sine omega t into omega, right? And what is v? It is f of t. Substitute in this formula. So we have f1c of omega, this is equal to root 2 by pi is common out, right? F of t, u into v. So u into v is f of t into cos omega t. Apply the limits 0 to infinity minus integration 0 to infinity v into du. That is f of t into minus, or I'll just take it as sine omega t into minus omega dt. Now the first term here, this will not become equal to 0 because cos 0 is not 0. Cos 0 is 1. We are going to substitute as upper limit minus lower limit. So as t tends to infinity, f of t is going to become equal to 0. So minus of when t tends to 0, it is going to become f of 0 only. So we have this term to be equal to minus of f of 0. And what about this term? This term, if you see, minus omega comes out, it becomes plus omega, and the remaining term is nothing but fs of omega. So we can write f1c of omega to be equal to root of 2 by pi f of 0 minus, since we have a minus here, and here we have plus omega fs of omega. Or I can rearrange and write it as omega fs of omega minus root 2 by pi f of 0. So this is Fourier cosine transform of the first derivative. So similarly, we can find the second, third and so on. But we are not going to get a generalized value because they are not going to be the same everywhere, or it is not following a definite pattern. So we have to find the second derivative, Fourier sine transform of second derivative. Then we have to again differentiate this for the second order, that is d square by dt square, right? So this is the Fourier sine and cosine transform of first derivatives. So I hope the Fourier transform of derivatives, the derivative of Fourier transform, the Fourier sine and cosine transform of derivatives is clear to you all. If you have any doubt, please comment on my comment box, and do like, watch and subscribe, and please share it to your friends. Thank you. Hope you have a good day.